So we're starting our turbo pump down. So welcome everybody. I hope everybody's summer has gotten off to a good start, if not. So yeah, so I hope everybody's done the readings like good students. So let's start with a general question. Back in the 19th century, obviously Boltzmann both made a big contribution to thermodynamics, but also started a big controversy about his thesis that he has proven that any closed system tends to equilibrium, which obviously, as he realized, had cosmological implications, since cosmos as a whole could be considered a closed system. And others drew from that the idea of the heat death of the universe. But as the reading says, in part, he derived some of his ideas, or seemed to have been partially inspired by Darwin's work, which of course is about the evolution of life on Earth, basically tending away from equilibrium to a greater and greater development of the biosphere. So my opening question, which is pretty open-ended, I think there's a lot of material to discuss, is did Boltzmann really prove what he said he proved? And second of all, how did he and others start to reconcile this with the evolutionary viewpoint of Darwin? So before we start, I have one more thing I need to do, which is shut off the air conditioning because it's too noisy. I'll be right back while you think about it. Okay, who wants to start? And remember, you've got to take the initiative and unmute yourself. Nobody?
Okay, I will.
Okay.
So the similarities to Darwin's theory of evolution in entropy, and I guess maybe one thing that that article didn't talk about what the second law of thermodynamics was, is that the entropy, all energy in the universe tends to go towards entropy, and entropy cannot be a negative value. That's the second law of thermodynamics, roughly. So how they reconciled it with Darwin's theory of evolution is they realized that Darwin was saying that through the genetic evolution of such species, that they can, evolve one way or evolve another way, but there can also be another evolution that sends them back to what the previous evolution was. So a it's not a far off thing where evolution is going to always continually happen. What Boltzmann was comparing it to was to say that, entropy will always occur unless there is another force that acts upon it to sort of cancel it out and provide to it. This is kind of jumping ahead and getting into the second article, but they list different laws and states to where basically, if you create energy through a destructive means, then you cannot reverse it in that matter. And there are other times where you create it in a non-destructive means, you can actually have the energy flow back and put it back into. This is similar to the theory of evolution that Darwin was talking about, is that when something evolves, that doesn't mean that that evolution is permanent. If a separate evolution happens that actually makes it go back to a previous state, then that's the it's still an evolution, but it is still a changed state, just of the same place that it was before.
Anybody else? Well, maybe we should take a smaller question, which isn't really a smaller question. It's very closely related to the first question. Based on these readings, what is entropy? Now, this is not a concept that Boltzmann himself introduced. This had been introduced earlier in the 19th century. But obviously, he and others are using a specific definition.
Hello, can you hear me?
Yeah, who's speaking?
Malcolm?
Okay, Malcolm. Go ahead.
Uh, um, I think the problem with entropy is that it's essentially a difference, in mathematical sense. It's like this minus this. And all the descriptions and language and thinking about it is substantial. It acts as if entropy is a thing when it's a difference between other things.
Yeah, who found this confusing? I mean, when you look at the formula, it always has that delta in it. The delta, of course, meaning a difference between two things. Um, Malcolm raises a very good point. Um, what are the things that it is a difference between? Yeah, go ahead. I don't see
Okay.
names and I can't remember people's names. So.
Ron Belsis, yeah.
Right, Ron.
Entropy is the condition where things when things change state, they always lose energy. So it's a process of gradually running downhill so that all energy in the universe becomes equal and there's no energy then left to do any real work. So it's a term to describe that process of things running down to
Right.
become equal temperature, if you like.
Right, but you're describing two things different. One is entropy. Entropy is not about a loss of energy because the first law is you can't lose energy, the law of conservation of energy. It's a loss of a certain kind of energy, free energy, right? That in any process in a closed system, the free energy has to decrease by that process. So that's one part of the definition. You're also referring to another different definition, which is that entropy increases as a state of equilibrium is reached. And then we also have to describe what do we mean by equilibrium. But let's just start the first one. People understand that we're talking about the decrease of free energy. So take a step back. What is free energy? How do you define free energy? How do you define, how do you distinguish between free energy and the other kind? Annette, I'll start calling on people.
Well, I don't know the answer to that question. I think of it more in terms of usable energy, energy that can be used to do some work.
Right. By who?
Maybe because it's somehow more opposed to equilibrium. And so it has the potential to move towards equilibrium.
Right. And Malcolm in the chat said free energy is the energy available to do work. But what's interesting here, we're talking about laws of the physical universe. And yet, if we look at these definitions, they're definitions referring to people. I mean, it's obvious. The question is, free energy is available to do work. Work for whom? I mean, in the technical sense, work, if you look at your freshman textbooks, work and energy are equivalent. But we're obviously using the term work, available to do work, useful energy. We're talking about available to us, useful to us. And that's one of the interesting things, because when I was learning this in school, I really scratched my head for months, and I was pretty embarrassed to ask, what the hell is free energy? You know, I mean, it sounds like a political term. But it's defined in a way that for the technology of the time and for our time was a very useful way to define it, which was how much work can you get out of this machine in this state? But what does that assume? I mean, first of all, what problems does that raise when we're defining a physical law in terms of usefulness to civilization here on Earth? But also, if you define useful energy in that way, what does that assume about, what does that assume? What assumptions are you making when you define useful work like that? I'm just going to go down the list if nobody volunteers. And by the way, to volunteer, because I don't see all of you on the screen, you really should raise your yellow hand signal or just start talking, because we're a small group and we don't need to worry about interrupting each other. If no one volunteers, I'll call on Craig. You're next on the list.
The issues I've always had with entropy are that it's defined for a closed system in which every space in the state space can be explored, and it finally equilibrates out. It doesn't work in nonlinear systems. It doesn't work in far from equilibrium systems. And I tend to go to the definition of entropy that it is only for closed systems in which the entire state space can be explored in a finite amount of time.
All right, but we're getting into very technical language, because then we have to define what a state space is. Go ahead, define what a state space is in one sentence.
The easiest one I have from my days of physics was to consider a billiard table. where are the positions and speeds at which any ball on the billiard table can go to. And it's enclosed by the ends of the billiard table. So, or the boundaries of the billiard table. So it's a closed system, and that defines everything that's available. It doesn't necessarily mean that we can define that for everything that's out there, especially when it comes to the non-equilibrium situations where you cannot, in fact, explore all the possibilities that are available to you.
Anybody else?
I was going to chime in on back to the original question of like what assumptions we make when we talk about like work as work needed by or done by people. I mean, just what it made me think about was like using, I don't know, that like work term or this entropy term as like a way of like humans relating with the natural world around them. So like math kind of like as like a language to describe a physical process that then they like use in their daily life versus, I don't know, like a more abstract mathematical like notion of nature and like the universe.
Could you give an
where
example?
For the first point or for the second point?
Either.
Well, I kind of think it maybe is like a theme of what we've been talking about in study group, where it's like I know there kind of is like a whole philosophical history of this argument of like, is the universe all just like math equation? Like, does it just all boil down to math equations, or is it just like a tool for us to like learn more about the world and make technology that makes our life easier? A specific example could be, well, I don't know. I feel like probably a lot of technology today uses it. Do you have one in mind? Where you're...
No, I was just pressing you to be concrete, because when we speak at a high level of abstraction, it becomes more difficult to convey what we mean when we use a concrete example.
Eric,
What abstractions refer to. Oh,
Hmm.
Peter, just let
okay.
Pam finish first. And do you want to take more time
Well,
to think of an
Peter, keep
example,
jumping.
and then we'll let Peter talk?
Yeah, sure.
Okay. Peter.
Yeah, I wanted to get back to the free energy question you had raised. So does this imply the state of the system and whether the free energy kind of gets dissipated in disorder and chaos, or whether the system in somehow it enhances or is captured by the system? Especially if you're talking about a biological system, the free energy in a biological system sort of generates a more intense focus and organization of energy.
Well, again, I'm trying to concentrate briefly on the definition. Let me, maybe I'll have to a little drop the Socratic method here. Let's take the machine sitting over there. Over there is our experimental room. I'm in our other room, control room. Before I pumped it down, it was filled with deuterium. Deuterium is an isotope of hydrogen. It's chemically identical to hydrogen. So if we look at the thermodynamics of that system, we would be asking, you know, what is the free energy available inside that vacuum chamber? So what you have is deuterium that's sitting there at 26 torr pressure. By comparison, we're sitting in 760 torr pressure. So this is somewhat lower than atmospheric, but not a vacuum. And it's basically at the same temperature as its environment. So what would we have to do to figure out the free energy inside that vacuum chamber? And what assumptions we have to use? All right. Elliot.
It seems like we would have to do some work to initiate any kind of testing of the free energy, or we'd have to basically free the energy in the chamber so that it would flow in some direction or another, and then we could measure that flow and the change in the pressures and so forth.
Well, in theory, I mean, if you're talking about the use of free energy, it's something that you should be able to calculate, right? Because what we're talking about in the definition of entropy is delta. So it's the change in free energy divided by the temperature. So we know how we can obtain the temperature. We can measure the temperature directly by various means. But how do we calculate the free energy knowing, well, how would we calculate the free energy? How would Boltzmann have calculated?
Have a guess and say that the free energy is available as either the kinetic or the potential energy. We measure that by temperature, as you've inferred, but the temperature relative to what? So it's got to be to absolute zero, the coldest possible temperature where we have zero energy. So the difference between your zero energy state and your current state would be the energy that's still available to do work. And that would be your free energy.
That assumes that we go outside the vacuum chamber, because inside the vacuum chamber, there is no absolute zero available. I mean, there is no cold reservoir available. To get free energy out of the heat content of deuterium, you would have to have a colder place to go to. All right, I guess I'll have to answer my own question. I mean, Boltzmann would say, look, there are two sources of free energy. Remember, that's energy available to do useful work. There's not any free energy available from simply the heat content of the deuterium, because the deuterium's at equilibrium with its environment. It's at the exact same temperature as the vacuum chamber, which is much more massive. But he would then say, what's the chemical energy available to do work, right? So you have hydrogen. Well, again, if all you've got is hydrogen, hydrogen does not react with itself. So he'd basically conclude you have reached a state of equilibrium. that if you introduce some oxygen from the atmosphere, for example, through a leak, then you would have free energy available because the oxygen and the hydrogen have the potential to combine to water and release energy, which could be used for anything. But we know, because it's our machine, that there actually is another source of free energy that wasn't known to Boltzmann or anybody at that time, which is that the deuterium nuclei can actually combine with each other, given the right circumstances, and release one hell of a lot of free energy, which can be used to do various things. So what I'm getting at is the definition of that definition of free energy, the free energy available to do useful work, has to do, it's not an objective measure. It's a measure in reference to our level of knowledge of the sources of energy available, or not only our level of knowledge, but our level of attention. In other words, if this deuterium was in a chemical lab and it wasn't inside our focus fusion machine, nobody would be really interested, would have a real interest in the fact that there's nuclear potential in the deuterium nuclei, because that's not what they're focused on. What they're focused on is like burning the deuterium for fuel, for chemical fuel. So that's one side, one side of the confusion that started to arise from the second law of thermodynamics is that the definition of free energy, while a very useful definition for technology, is a definition that's relative to human beings, their technological goals, and their state of knowledge. So that the free energy of the deuterium changes on the basis of our knowing that there's nuclear energy potential available for that. So let me end that lecture. And what do people think of that? Is that clear, or have I confused everybody?
I mean, just going back to what I said, Eric, I mean, I don't think the energy in the deuterium is free unless you, as you put it under the right circumstances. Right now, it's at equilibrium, so it's effectively bound inside the container with no work possible. But you have to actually do something from the outside to the system to generate this potential into a usable form. I should say to transform, make it transformable.
Well, but that goes for chemical energy too. When a leak introduces oxygen into our machine, the oxygen does at room temperature have the potential for latching on to the metal coating of the machine. But it doesn't have the potential at room temperature of combining with hydrogen. For oxygen and hydrogen to combine, they have to be at a much more elevated temperature. You need a spark.
Nonetheless, you're opening, the leak is opening up the system. And if the conditions of the combined systems are right, then you have the potential for work or free energy.
Right, but what I'm saying is, just like you have to raise the temperature of the little plasmoid up to, hundreds of millions or billions of degrees to burn deuterium through its nuclear forces, even oxygen and hydrogen, which would have, in Boltzmann's definition, potential free energy. So free energy would be includes potential energy, that would have to be liberated, would have to be raised to whatever the ignition temperature is. It's pretty high because we're not worried about having an explosion from our deuterium tank just because we don't allow sparks here. So
you're saying that the free energy includes potential energy, not even though potential energy is basically bound until you find a way to unbind it from its form or containment.
yeah, in other words, free energy is the energy potentially available for work. It doesn't mean that it's doing work, but it means it's available. So the difference between hydrogen and oxygen in a tank is they have chemical potential energy. If you combine them to water, I won't say water doesn't have potential chemical energy. It does, but it's much less because you've combined them, they're bound very tightly together. So that's one limitation on this free energy definition. But I think it's very interesting to get to the other question, which is defining the second law of thermodynamics is all systems, all closed systems tend towards equilibrium. So let's get into the question, what is a definition of equilibrium? How can we measure whether something is further or closer to equilibrium? Or, what is the state of perfect equilibrium that things are tending towards? All right. Who hasn't talked? Let's see. Just a second. Oh. Has everybody talked? Warren. Yeah, you came late, but not too late to listen to that question. What's your answer on defining equilibrium or how we measure equilibrium? Distance to equilibrium.
I came too late.
But you did the reading, didn't you?
No, I did not.
Oh, you have a black mark. All right. So anyone who's done the reading since you've all spoken once, volunteer? Yeah, go ahead, Ron.
Yeah, by our previous discussion, we said that the free energy is the energy available in the system to do work. So by definition then, if there's no free energy left in the system, it has all been used up, and therefore the process has reached the equilibrium.
Okay, so here you're defining one term in terms of the other one, that you're saying equilibrium is the state of zero free energy, right? Okay, Brian, you wanted to speak?
Sorry, I was dealing with the customer. Can you repeat the question for me?
Oh, I'm sorry. I thought that your name appeared, so I thought you had unmuted yourself.
No, I have the shop open today because it's an event weekend. But yeah, go ahead and repeat the question. I'll see if I can answer
Well,
it.
I'm working too. Oh, the question was, and as I say, this is not just for Brian, for anybody else who wants to volunteer, was, define equilibrium. Now, Ron has defined equilibrium in terms of the other term, free energy. as the state of zero free energy. I'm asking, can you define equilibrium in a way that doesn't refer to free energy?
Well, equilibrium in a way that doesn't refer to free energy is when both sides have the same amount of potential and kinetic energy, and therefore are in a almost a state of stasis, so to speak, from the observable eye, but aren't truly in stasis.
Okay. Martin has something in the chat. Martin, you want to read what's in the chat?
Yeah, I just wrote equilibrium is a state where entropy is not changing.
Entropy is not changing. Okay. So that's a dynamic. Entropy is not changing. And Brian, yours was also dynamic because you were saying something's in stasis, but which is not changing. But in your definition, what is not changing?
The transfer of energy or the flow of energy, the entropy from one object to another.
Okay. So you're saying the state of equilibrium is when energy flows are not changing?
Essentially well, if you actually go back to magnetic fields, it could even be said that when the fields are, not being affected by any other force.
Okay. Well, I would correct that. In other words, if energy flows are constant, you're not at equilibrium. Equilibrium can be defined in terms of energy flows, but it's the state in which energy flows don't exist. When energy flows are zero, then you can define a state of equilibrium. So what's interesting about this, to me, is that definition is objective in the sense that, at least in theory, you can measure the energy flows in a system in a comprehensive way. And therefore, it's not dependent on whether whether the free energy is available for our use. So the energy flows, energy flow, basically, we're talking about energy flux in technical terms, is the amount of energy flowing through a given area in a given amount of time. So its power per unit area is energy flux. So in a state of equilibrium, the net flow through any surface is going to be zero. So, okay. Now, when we're talking about your definition, Ron, entropy not changing, that's correct too. Basically, equilibrium is a state of stasis in which all of the measures that are based on energy are unchanging, which is why people popularly refer to the heat death of the universe. Dead, nothing's happening. But in fact, it's a very common situation in which energy flows get to very low levels. So that becomes very interesting in terms of the subsequent more than a century of dealing with thermodynamics. because I think it was, I'm sorry. I'm not sure which of you said, but it was correct that this tendency to move towards equilibrium doesn't always occur. And that was what, to sort of give a historical spoiler, which isn't a spoiler if people have read my book. In the 100 years after the work of Boltzmann and Maxwell, in the mid to late 20th century, we have the development of non-equilibrium thermodynamics, which is the study of systems that are far from equilibrium, have very high or intense flows of energy, again, like our machine in the next room. And what Nobel laureate Ilya Prigogine and others demonstrated is that their behavior is very different than the systems close to equilibrium that were being studied in the late 19th century. And it's not totally a coincidence, it's not at all a coincidence that a century separates these two periods of study, because if you look at the technology that was being used and developed in the 19th century, and we're talking about the perfection of the steam engine and steam power, which was not, even though it was in use from the 18th century, was not actually made highly efficient until the 19th century on the basis of the development of thermodynamics. All of those technologies, both the chemical technology, power technology, operated very close to equilibrium. And that was deliberate because that was the best way to control those processes. While in the 20th century, and especially in the second half of the 20th century, our technology started to deal more and more with systems that were very far from equilibrium, both through the study of biochemistry and biophysics, studying the products of biological evolution, which are all very far from equilibrium states, including the atmosphere we breathe, which is nowhere near chemical equilibrium, and the development of technologies like ours, high energy intensity technologies, which again operate far from equilibrium. So okay. So let me just ask, first of all, is there any questions on what I just said? And I have to switch briefly into lecture mode before we go on.
So is this the territory of negative entropy that you're discussing?
Not really. It's not a useful negative entropy doesn't have a very useful entropy.
What is
Entropy itself is not it's not on a fixed scale like temperature. As one of you pointed out, entropy is defined as a change. So entropy, if you go to a lower state of entropy and the change is the change in entropy is negative. If you go to a higher state of entropy, it's positive. There's no such thing as negative entropy in itself because there isn't an absolute entropy scale.
So what term do you want to use to describe 20th century thermodynamics as opposed to 19th century?
Well, the term that people do use is non-equilibrium thermodynamics.
Okay.
So, and it's not an exact term because, of course, all thermodynamics deals with states that are not in equilibrium. Equilibrium itself is pretty boring. The question is, how far from equilibrium are you? Well, we can't get into this. We don't have time to get into this today, but I always was planning to have more than one session on this topic. So we're going to get into it in the next session, which shouldn't be too far off. We got to wind this one up at the end of the hour, which is very soon. But there is an objective definition of far from equilibrium. And it basically means if the energy flows, the time scale of energy flows through a system are short compared with the time it takes the system to decay to equilibrium. In common systems like chemical reactions, boiling water, and so on, the energy flows are sufficiently small that the time to reach equilibrium is the characteristic time of the system. But in systems like, the focused fusion device, almost all plasma systems, like processes like lightning strokes and so on, the time scale of the energy flows is very short compared with the time scale to reach equilibrium. And that's true inside living beings too. The time scale of our chemical reactions are very short compared with the time scale to reach equilibrium, which is essentially the time it takes a dead body to cool off. So in those systems, some of the assumptions, mathematical assumptions that Boltzmann made and are very useful to make for a whole variety of close to equilibrium systems, those assumptions don't actually apply. So we'll get into that in the next session. But before we wind up, as I say, it's basically going to be a continuation of this session with a little bit more getting into out of chronological order discussion of 20th century thermodynamics. But I do want to ask people briefly, I know people are going on vacations, they're taking off and so on. On the other hand, a lot of people don't unplug from the internet when they go on vacation. So if we go like 3 weeks from now, since you're not doing more reading, it's okay for me, but that gets into July. Is that going to be bad for some of you because of vacations? Or is 3 weeks from now good for continuing this?
Good for me.
You should really just speak up.
Okay.
It's bad for you.
It's bad for me.
Okay, what would you prefer?
Bad for me too.
I think either 2 or 4 is okay. It just happens that 3 is.
Okay. How about 4 weeks? Is anybody bad with 4 weeks?
Let's see. Let me make sure I didn't
Is that
misspeak.
the-
So is that
So,
July?
It's
4
bad too.
weeks. Can somebody?
Is that the weekend of the 20th of July?
It
4
probably
weeks.
is.
Yeah, 4 weeks is the 20th.
Okay, so that's bad for me too. I could do the 27th. but I could do the 27th or the 6th. But of course, if it works for everyone else, go ahead.
Well, all right. 27th is still just a month away. How about the 27th? Is that bad for anyone? Okay, great. So I'll see you all on the 27th. Maybe we can go for an hour and a half then, if that's not too long for people. And as I say, we won't have more readings. We're just going to be working our way through the implications of this. Because as you can see from the readings, it was seen even at the time as a really complicated problem. And when entropy was first introduced, you saw one of the leading people say, yeah, entropy. That definition, entropy means precisely nothing. So this is worth chewing over because it's really critical for understanding the development of physics in the 20th century, as many of these issues are raised around the second law, and it gets into how people move to quantum mechanics and other forms of 20th century physics. So, okay, well, great. Thanks for coming. And if people think about more questions, by the way, it's perfectly all right in between sessions to send me the questions if you think of things, and we can use them for discussion the next time. So I'm going to sign off and get back to exploring physics experimentally, and I'll see you all in July. So have a great month.
Okay. Bye, everyone. Good
Bye-bye.
luck. Thanks,
Later.
Eric.
Take
Bye.
care.
Bye.